If you want, I can share my screen. That's not a
problem. No. I'll share. End-to-end systems and walkthrough. Okay. Are we going to the concept and then how part, right? First we'll go to the concept.
Yes.
I'm sharing my screen. Okay. Beautiful. Now we are into this module 15, end-to-end system design walkthrough. Okay, beautiful. Why this module is covered in depth? Module 15 ties all the previous modules into a complete interview-ready walkthrough. Interviewers evaluate not only your architecture but also how you reason step by step and communicate decisions under constraints. This module builds the ability to run the full system design discussion confidently. Very important. The goal is to demonstrate senior level thinking, clarify requirements, define scope, choose the right components, handle failures, and explain trade-offs clearly. Right. So now, applying all the concepts together, how we are going to do that? What? Applying all concepts together means combining requirements, decomposition, data modeling, scalability, performance, reliability, security, observability, and operations into a single coherent system design. Why? Real systems are not designed in isolation. A good system design must balance multiple dimensions together instead of treating each topic separately. Right. When use this approach in system design interviews, architecture reviews, technical planning sessions, major system redesign discussions, production readiness evaluations. Example, our use case, food delivery. Designing the order lifecycle from placement to delivery, including payment, tracking, notification, reliability, security, and observability. Plain English understanding. End-to-end system design is like explaining a complete business journey from start to finish. You do not only say which tools you will use. You explain what the user needs, how the system responds, where data moves, what can fail, how the system scales, and how teams operate it safely. Engineering view. A complete system design walkthrough connects requirements, scope, core user flow, system components, data model, API contracts, communication patterns, scalability strategy, performance strategy, reliability and fault tolerance, consistency and data integrity. Yes.
Sorry, Sridhar. Let's take a pause after some points. Okay. And let's have a discussion there.
Sure.
That means it will look like realistic, not just reading the theory part only.
Right.
It should be some realistic thing should be there. What's your opinion there? Stuff like that.
Yes.
So that you can recall everything.
Correct. So now, fine, we'll start again now. A complete engineering view. A complete system design walkthrough connects requirements, scope, core user flow, system components, data model. So now we'll have a small discussion on the 5 subtopics. Requirements. Okay. Now, first of all, for any application to be developed, we need to know what are the requirements. If the requirements are not defined, then what we are going to develop, we don't know. It will be blind. Okay. So the requirements, we are just going through we're just going to do a walkthrough of all the requirements from the end user point of view, like what he really required out of this whole thing. Something called, he said that everybody is going online, even I want to go online. And then we had a chat with him and he explained few things what all he wanted, that we are going to go through. And then scope. Yes, now he may give hundreds of requirements, but we should see whether everything, what all will come in scope. The reason here is probably we may not be able to do everything whatever, or all the, we may not be able to meet all the requirements what he wanted. So we may offer him, okay, we are going to do this in a phased fashion, in a phased manner. Okay, in phase one we are going to cover these things. So like this, what is the scope about the whole product will be discussed at length. And then how core user flows, how the user is going to use application, the flow of the whole application will be discussed from end to end. And then what are the system components we are going to have? System components of, for example, this I mean, this, boutique project which we are going to take up, those will be discussed at length. Then again, data model, yes, how the data will flow, what is the data flow and communication, how each one is going to interact with each other. So all these things, this will be more of a technical walkthrough from probably a BA's point of view, or a architect point of view, or maybe to some extent an end user point of view, how the data is going to flow. All those things will be discussed under, I will be having, a walkthrough under the topic called data model. Now, we have some more points under engineering view, like for example, API contracts, communication patterns, scalability strategy, performance strategy. Now, yes, API contracts. Now, first of all, there should be a clear contract between what we're going to ask and what the application is going to give. Those has to be very clearly defined. So whatever contracts we have agreed upon, only those will be provided, or input will be on, and we get the output from that.
Question,
Then,
question here.
please.
API contract happened in which path? Because if we require some contract, it should be there should be some parties. Am I right? You understand my
One.
point?
Yes. Okay. Okay. The contract is always between two parties, right?
Yes, two or more parties. At least
Two or
two
more
are.
parties. Mm. So now the question is under, which two parties are going to discuss, like which two parties will have this contract?
Yes, yes. Two or more parties which you can consider.
Okay, two or more parties, right? Okay, fine. Fine. Okay. In fact, the day what we were discussing is yes. See, it is okay. Anyway, general thing is it's a formal agreement between, for example, say two services, services A, services B. For example, when we say services, we can say between the order service and the payment service. Once order service is executed, then the payment service. Okay, the contract is the payment service has to get enabled only when the order services is completed. In the same manner, the delivery service contract is such that the delivery service has to get started, or it should be up and running only when an payment order service is executed. So there we set the boundaries, or we set a policy that after so.
Yes, here you can just keep it simple, Sridhar.
Ah,
Means we have a front end where user is able to interact, am I right?
correct.
And our API is there, am
Ah,
I right?
ah,
And we have some external API as well, am I right?
ah.
So you need to define the contract. Yes, but API will accept as from a front end, as a, you can say, as a request, post request, am I right?
Okay,
And what means front end will get against that request, am I right?
okay,
So that based on that, front end person can design
okay,
their code and write the code there, am I right?
okay,
So this API contract tell that thing. Hey, if you need to request a backend, these are the API. Then you
okay.
need to means do this way,
Oh, okay, okay.
which we discussed earlier as well. Am I right?
Okay, 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 okay.
Okay, go ahead,
Okay,
please.
fine. Okay, fine. Okay, now uh, coming to communication patterns. Okay, communication patterns. What we can say is like in a simple way, probably in a distributed environment, how the communications are conducted between the distributed systems. So, for example, will it be an asynchronous system, asynchronous communication, or synchronous communication? Those will be discussed at this level.
Yes,
Synchronous
yes,
and asynchronous communication patterns.
as well
Fine.
as this event driven as well.
Even yes, yes. Fine. And then next is scalability strategy. Yeah, very important. Now, how we have designed our scalability strategy. Yes, we are going to we started our application thinking that okay, there'll be some normal around say 5K to 10K users in a week, and then gradually it will increase. Yes, the expectation is probably once it goes full online with all key features in place, somewhere down the line, somewhere maybe after 6 months or 8 months, we are expecting around 5x increase in the traffic, in the orders. So if that is the case, how our scalability strategy is designed so that the application runs smoothly without any hiccups, or whatever we have planned for, it should work in a consistent manner. So for that, what all scalability features are planned for. So all those will be discussed at length during this phase of scalability strategy walkthrough. Whether initially are we going for say vertical scaling, or later maybe after some time depending on the need, are we going for a horizontal scaling. So all those strategies will be thoroughly discussed at length, or a walkthrough will be done. So at every step, probably at every step we are going to go in a phased manner. And another very important thing here is, let us say on few occasions, or on some of the occasions, if there is a huge traffic, that may be a one-off case. Just because there is huge traffic on a particular day, it doesn't mean that we should rush and then quickly go for a big scalability. No. We have to just see the the patterns in that spikes, and see whether it is consistent or it is a one-off pattern. So how our scalability strategy is addressing that issue. So yes, it is a very vast topic, very interesting and fantastic topic to discuss at length. And then those will be now seen whether it is falling in line with our future plans or not. That is scalability strategy. Then performance strategy, very important. Today, let us say now, if I place an order, from order to deliver, an order, not delivery, order to checkout. Say it is under some 20 microseconds. Now, once this is with some, you say 5K users in a week or 10K users in a week, and gradually increase. Now, after 6 months, let us say now it is reaching around 75K to 100K users. If it is somewhere around what was 20 milliseconds, if it is reaching somewhere around 22 to 25, or somewhere 26 milliseconds, yes, it is okay. But suddenly, if we see the performance going down, for example, it is taking more than 100 milliseconds, then definitely there is a problem. So in order not to encounter those type of performance issues, we have to see whether those strategies are also documented or discussed, so that the user should not feel any difference. For him, it is the same application, the same user experience, very is able to come out of the whole application after ordering, logging in order within around 20 to 25 milliseconds, which he got used to for the past say 6 months. So whether those are all taken care of or not will be now discussed in our performance strategy walkthrough. Then reliability and fault tolerance. Yes, the application has to be reliable 24 bar 7 anytime. The user should be able to rely on our application for whatever needs he wanted to. And then fault tolerance. Yes, for example, if anything goes wrong, yes, probably if I say payment, there's a delay in the payment. So how quickly we recover from that fault, and then probably say we put in place the retry options. For example, the user can try for 3 times. Beyond that, if it fails, then we can just display a sorry message and then come out of the whole application. But find out what was the cause of the problem, learn from that problem, and then see how next time the problem doesn't appear. So all these things, where the application may encounter a fault, so all those strategies will be now discussed in this walkthrough.
Yes.
Yes.
Good. Good. Good.
And then consistency and data integrity. Yes, consistency. Now let us say our application is used across, say for example, South Asian countries. We are getting to all the South Asian customers, and if I place an order, let's say the stock is getting reduced, the very second the other end of the country, somebody is trying to place an order, he should be able to get the new reflected inventory. For example, in this case, inventory stock being shown as, for example, -1. So you should see the current status within few microseconds. Here, the thing is, for example, if I'm seeing one particular item X as current stock as 10, everyone should see the stock as 10. Me seeing 10, somebody seeing 8, somebody seeing 9, that will cause a big problem. So throughout the whole experience, the user should have the consistent data getting reflected everywhere. And data integrity, whatever data the user keys in, that should be maintained and stored. There should not be any mix-up in the data. For example, let's say user profiles. The user is giving all his details. There should not be any loss of data. And then, or somebody should not get into somebody else's data and then manipulate it. So whatever data is keyed in, or the products for that matter, so that data integrity should be very, very, very well preserved. So yes, the user or say the admin person should feel confident. The moment I enter the data, I know my data is safe, no manipulation happens, the data integrity is very well maintained throughout my application. So that is data integrity. And then security and access control, they are another very, very important aspect here. We have to really spend more time under this walkthrough called security and access control. Yes, security, whether our application is safe while we are doing any payments, while we are doing a payment services, is it very well secured? Is end-to-end encryption put in place? So we have to ensure that no hacker will tap the transactions in between and then try to hack the data, or get into my bank details and then no hack all the information. So as the application open wide open to any user, security will be given a very, very highest importance. And yes, this importance is given right from day one of the design of the application. It is not towards the end of the application. Right from day one, the security aspects also will be thought of, very, very, very clearly thought of, and then the whole application is designed. This ensures that my customers are loyal to me, and because in one breach, I can lose millions of customers. So to ensure that I don't lose my loyal customers, I will put whatever security is in place. So that will have a thorough walkthrough, and the users, I mean, the experts are all allowed to test my application in various ways. And once they're satisfied, they can certify that yes, all the loopholes are well taken care of. So those will be discussed at length in the security security walkthrough. And coming to access control, yes, this is also another crucial thing. For example, an end user. An end user, what he's supposed to do? He's supposed to just place an order, do a payment, and get the item delivered. Now, his access is very limited to viewing the orders, viewing the products, placing the orders. The end user cannot be allowed to modify the product data. For example, product data he cannot modify. At the same time, he can modify the order quantity. He ordered some 10 numbers of item X, but I should allow him to modify that 10 to probably 5 or 20 or 1, or he can say 0 and come out. So he has to manipulate, he has access control of certain things where he can do a read and write. Whereas in some case of example, the best example is the product name or the cost price of it. He can't go and manipulate the data. So there I ensure that the access controls are very well designed so that each user knows his access control responsibilities, and they are within that framework. An admin person, one is authorized to add the products, can go and add the product. He is authorized to delete the product. He is authorized to delete the product or modify the product. But again, here it depends on the company to company. I may have in my company, for example, out of some 6 people, only 2 people can go and add the product, 2 can only go and alter the product, 2 can go and delete the product. So like this, also it can be designed, but otherwise, yes, this is the core thing is whether whatever access we are giving to the users can be anybody, the admin users, the main administrator user, or the end user. So their access controls, or whether it is well defined or not, will be discussed or seen through in our walkthrough of this. And then coming to observability and monitoring, yes, again, this is right from day one. These are all some of the tools where we just keep monitoring the health of the application. Uh, Generally, what happens is initially everything is fine, no worries, because limited number of users, limited logins, and everything is going well. But if there's a sudden spike, if something goes wrong, or some user is complaining, or some of the users are complaining that no, your application is getting slowed down. If I go to so and so page, it takes so much time to bring up the product, or when I'm doing a payment, I'm encountering so much of delays. So when somebody is complaining, people are complaining, blindly I cannot just go and tweak my system with more RAM, or add more cache, or add one more server. No, that is a solution. I should know where what is going wrong. So how will I know? I will know that only when I put certain things in place. For example, like observability and monitoring. Yes, I have some trace files, I have some log files. Okay, so that data will help me to narrow my focus on the problem area, and then see the genuinely it is a problem, then see what action can be taken. I just try to tweak with the existing facilities, see whether that is improving. If not, again monitor for some more time and then take the necessary action. So without these tools, observability and monitoring in place, I cannot have a blind guess. Okay, because of this, the problem might be there. So let us go and fix that. That is a little foolish thing to do. So these tools help me to take a pinpoint the problem area, and see that what good solution or better solution can be given to overcome that problem can be known from this. So in this walkthrough, we just understand the nuances of the performance with the help of trace files, log files, and other things. Then deployment and operations. Deployment is in today's fast-paced development, we need to keep on adding new features to the users, so that they should not just jump to some of our competitors. So here the deployment happens probably in many cases once in 3 days or once in a week. So we keep deploying new features or new thing, or maybe somebody has encountered a bug they reported, so I rectified that. So that calls for a new deployment. Yes, again, there are various kinds of deployments, but general deployment is was some new development I have done in the application that has to get percolated to all the end users. So I just send a warning email stating that within so and so time a server will be down, and then I'm going to deploy my latest application in a smooth manner such that the other part of the world of users should not feel any glitch. They should be able to use it, run it without any strain showing that something is going wrong. To some extent, yes, there are some tools in place which will not hold any user at ransom. They will be able to continue their work, but in the background, the upgrades will take place. So that is deployment and operations. Then trade-off reasoning. One classic example is just because my performance is slow, I just simply cannot increase my RAM. I should see whether what are the other trade-offs instead of simply improving the RAM or increasing the cache. So those trade-offs we have to see whether go for vertical scaling or horizontal scaling. So there we often have a discussion on the trade-offs. Then the team comes to a conclusion. Then they take that decision that okay, so and so thing has to be done, even though others are outweighing the decision what we have taken. But at the end of the day, it is we who take the calls and who decides what is better for the company and for the growth of the company. So we put all the pros and cons against each topic. We put the pros and cons, debate on that, and then we reason it out and then narrow down to one solution. Probably, maybe in some cases, is adding a resource is going to ease the problem. In some cases, there may not be any budget, so they may request us to do some tuning with respect to the existing system. So various reasons will be there to see whether to go for a new system, whether improve only the cache or improve the RAM. So many things, the parameters are to be discussed. When that is done, then they take a call on going for a change. So this is an overall view of your trade-offs. Mm.
Yes. So basically, with this help of this engineer, we will cover all the things which we discussed earlier. Am I right?
Mm, mm.
Now we can move forward, and wherever we require, we will means discuss more. But
Okay.
thanks for your better explanation of this.
Yeah, fine. Why end-to-end walkthrough matters? Yes. An end-to-end walkthrough shows how a system works from user request to final business outcome. Correct. Why? Interviews and architecture reviewers want to see whether you can connect theory to a real system. Interviewers and architects, yes, architecture reviewers want to see whether you can connect theory to a real system. Yes, when use this whenever a design question asks you to build a full product or platform. Use this whenever a design question asks you to build a full product or platform. Okay. Plain English understanding. A strong answer should sound like a guided tour of the system. The listener should understand what user does, which component handles what, where data is stored, how services communicate, what happens when during the failure, how the system is monitored, and then how the system can evolve later. Example. For food delivery system, do not start with only I will use microservices. Start with user journey. User opens app. User selects the restaurant. User adds the item. User places the order. Payment is reversed. Payment is reversed. Then restaurant confirms. Delivery partner is assigned. User track order. Users track order. Order is delivered. Notifications are sent through the journey. The map that and the map then map this journey to architecture. Okay, fine, step by step. Oh, step by step system design reasoning. Okay, fine. What? Step by step system design reasoning is structured process there that starts with a problem facing for framing and ends with operational readiness. Why? Step by step reasoning prevents missing critical requirement and make decisions defensible. 1 minute. Step by step reasoning prevents missing critical requirements, correct, and make a decision defensible. Okay, something goes on when we are trying to defend that decision. Okay, but that should not be the case. Okay, fine. When at the start of every system design discussion, use cakewalk through. Okay, clarity requirements. Daniel MVP identifies flows, decomposes services, defines data model, chooses a communicationable part patterns, plan for fourth failure, second and third are eliminated. Sorry. Okay. Readiness. Okay. 1 minute. Yeah. Okay. Step by step system design reasoning. Okay. What? Step by step system design reasoning is structured process that starts with problem framing and ends with operational readiness. Why? Step by step reasoning prevents missing critical requirements and makes decision defensible. When? At the start of every system design discussions. Okay. Use case walkthrough steps. Okay. Clarify requirements. Define MVP. Identify flow. Decompose services. Define data model. Choose communication patterns. Plan for scale, failures, security, and observability. Plain English understanding. Instead of randomly jumping from one database to cache to microservices, follow a disciplined order. This makes your answer clear, calm, and professional. From engineering view, a strong walkthrough usually follows this pattern for this order. Clarify requirements. Yes. Define scope and assumptions, identify core user flows, define MVP, decompose the system. Now, coming to clarify requirements. Yes, if the requirements are not clear or not clarified properly, then definitely the project itself cannot take. We should be.
We will discuss in detail in a sequence means
Okay.
file, in this file only. So
Okay.
you can just go on through.
Okay, fine. Then model, okay, fine. Decompose the system, model data and state, define APIs and contracts, choose synchronous or asynchronous communication, choose scalability, choose performance, address reliability and failures, address consistency and integrity, address security, address observability, address deployment and operations, explain trade-offs clearly. Okay. Clarify requirement. What? Requirement clarification means understanding what the system must do and how well it should behave. It must behave. Why? Without requirement, correct architecture becomes a guesswork. Correct. When at the beginning of every system design interview or architecture discussions. Fine. Functional requirements. Functional requirements describe what the system should do. For food delivery, users can browse restaurants and menu, users can place orders, users can make payments, restaurants can accept or reject orders, delivery partners can be assigned, users can track delivery status, notifications are sent for major updates. Fine. Another important thing, non-functional requirements. Yes, very important. Non-functional requirements are describe quality expectations. Example, order placement should be reliable. Payment should be strongly correct. Menu browsing should be fast. Tracking updates should be near and should meet real time. Very important. Yes. System should handle failures gracefully. Correct. Gracefully. System should be observable. Yes. Sensitive data should not be protected. Correct. Now, common mistake what we do, jumping into technology choices before clarifying requirements. Correct. all jargons we use. Fine. Okay. Then defining the MVP score. Okay, MVP. MVP score defines the smallest useful version of a system that solves the uh, core problem. Why? Designing everything at AI one leads to have over engineering and unclear answers. Then one minute, designing everything at once leads to over engineering. Okay, yeah, fine. So MVP scores define small and useful version of system that solves the core problem. Why? Designing everything at once leads to over engineering and unclear answers. Correct. When after requirements clarification and before detailed architecture. Okay, fine. Now it's clear. Okay. So food delivery MVP. A reasonable MVP may include restaurant menu processing, order creation, payment processing, restaurant confirmation, delivery assignment, order status updates, basic notifications. Yes, correct. We expect that. Out of initial scope, okay, what is missing here? Like the first design may exclude recommendation engine, advanced analytics, correct, multi-region, active architecture, complex loyalty programs, IA-based delivery prediction, then advanced fraud detection. Engineering view. MVPs does not mean poor design. It means that the first class version should be simple, correct, and evolvable. Okay, fine. Good MVP design should include clear data ownership, clear contracts, clear state resolution, basic security, basic observability, safe deployment. Oh, deployment also matters a lot here. Okay, fine. Safe deployment. Okay, identifying core issues. Fine. A user flow is a flow path. Is the path the user takes to complete a business action successfully. Why? System design should be anchored in a real business behavior, not only on components. Okay, fine. When before decomposing the architecture. Okay, fine. And when that is done, decomposing the architecture. Main food delivery flow. User browses menu. User places order. Payment is processed. Restaurant confirms order. Delivery partner is assigned. Order status is executed. User reviews notification. Once notification, order is delivered. There can be small delay. Sometimes there can be a delay in the notification, but still you go deliver and then later we'll get the notification delivery. Okay, fine, right? In the again engineering view, each user flow reveals required APIs, required data, required services, asynchronous pattern, failure point, consistency needs, observability needs. Okay, good. Observability has come here at least. Okay, decomposing the system. What system decomposition means is splitting a system into a logical representation or components. Why? Clear decomposition notes makes it design undesirable. So understandable, maintainable, and scalable. When after identifying users flows and requirements, what are the core components? Okay, clear. Okay, core components are for a food delivery system: API gateway, auth user service, restaurant menu service, order service, payment service, delivery service, notification service, event bus or other queue, primary database, cache, observability, patterns. Very important. Yes. Okay, fine. Now, engineering view. Each component should have a clear understanding of the agents. Example, order service owner orders for life cycle on correct. Order service owns order life cycle. Problem service owned by payment cycle. Delivery service owns delivery assignment as assess and updates. Notification service owns communication with users. Notification service owns communications with the users. Some confusion there. We'll clarify that. Okay, fine.
here we are using single responsibility, solid
Ah,
with.
okay, 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 okay. 1 minute. So here, okay, fine, right. Scalable. Okay, fine, right. Core component for food delivery system, API gateway, auth user service, restaurant menu service, order 1 minute, API gateway. Okay, sorry. Auth user service, restaurant menu service, order service, payment service, delivery service, notification service, event bus queue, primary database, okay, cache, observability platform. 1 minute, something is missing here. Order, payment, delivery, notification, event bus queue, primary database, which will be handling, okay, order cache, and then observability platform. Oh, auth is already the second. Okay, fine. Auth. Okay, auth user service. Okay, fine. Right. Engineering view. Each component should have clear ownership. Yes, very important. Order service owns order life cycle. Payment service owns payment life cycle. Delivery service owns delivery assignment and updates. Notification service comes communicated owns communications and communicate with users. Restaurant menu service owns restaurant and menu data. Very clear boundary support. Important principle. Do not over decompose too early in the early stages system. A model monolith may be better than many microservices. In a mature high-scale system, separate services may become justified. Correct. You should not automate everything. Yes, okay, fine. Then data modeling and state thinking. What? Data modeling defines the important entities, relationships, and state transitions in the system. 1 minute. Okay. Data modeling declines the important entities. It declines important entities, relationships, and state transportation in the system. 1 minute. Determine, define the important entities, relationships, and state transition. Okay, state transition. Okay. Which state to which state? Okay, fine. Sorry, got it. Okay, fine. Why? Poor data modeling cause integrity problem, unclear ownership, and difficult scaling. Yes. When after identifying services and flows. Okay, now core entities: user, restaurant, menu item, order item, payment, then delivery task, and then notification. Okay, order state example, created, payment is pending, payment is confirmed, preparing, quantity out for delivery, and then delivered. Okay. Engineering view. Order lifecycle must be controlled by explicit state transitions. Example, created, payment pending, valid. Payment pending, confirmed is valid after payment success. Correct. Confirmed. Cancelled may be valid only before preparation starts. Correct. Delivery. Preparing should not be allowed. Oh. Some confusion with Deepak here. See now why he says delivered, preparing should not be allowed.
Let's say if it's delivered, then it's already delivered. Why we will go for preparing then? It's done.
Uh-huh.
Cycle is already done.
Oh, okay. Already done. Okay, fine, right. Delivered or preparings should not. Oh, in that context, he's telling. Oh, okay. Got it. Okay.
We are repeating this. We are revising everything. We already covered these things.
Yeah, great, but it's just going through. Then data integrity focus. Critical part includes payment result, order confirmation, delivery assignment, refund status, order completion. Fine. API and contract linking. What? APIs and contract define how clients and services interact. Why? Clear contracts prevent confusion. Exactly. Misuse and integration failures. Very true. When defining system boundaries and service communication. Example: post orders, get orders, post orders, order ID, patch orders, order ID, then post delivery, patch delivery. Engineering view. A good API contract defines request fields, response fields, error codes, how idempotency behavior, retry behavior, authorization requirements, validation rules. Example contact decision post the orders should support an idempotency key. So duplicate requests do not create duplicate orders. Okay, beautiful. And 10 communication patterns. One, communication patterns define whether services call each other synchronously or communicate asynchronously. Very good. Why? The wrong communication pattern can make systems slow, tightly coupled, or unreliable. Why? The wrong communication pattern can make systems slow, tightly coupled, or unreliable. When when designing interactions between components, very important. Synchronous communication use when the caller needs an immediate answer. For example, I place the order from a waiter in the room, in the hall. I go and sit. uh, a waiter comes, and then he orders in the kitchen, and I wait for the order. Fine. Then synchronous communication, when the when the caller needs an immediate answer. Sorry, example, order service calls payment service for payment authorization. Asynchronous communication. Okay, use and work can continue in the background. Notification service example is best example I can think of. Order confirm event trigger notification service. Order confirm event trigger delivery service. Analytics consume order events later. Yes, these things are in the background, so I need not have a synchronous communication. It will be asynchronous communication. Fine. Engineering view. Use synchronous communication carefully on critical paths. Use events when decoupling and resilience are more important than immediate response. Okay. Scalability thinking. What? Scalability thinking defines how the system will handle growth in traffic, data, and users. Why? System must scale the right parts, not blindly scale everything. Correct. Correct. When after baseline architecture is clear, likely bottlenecks in food delivery, restaurant slash menu reach, order rates during peak time, payment gateway latency, delivery assignment processing, notification bursts, then tracking the updates. Fine. Scaling options, cache popular menu data. Use read replicas for read heavy data. Scale stateless services horizontally. Increase event consumers for asynchronous workloads. Optimize database indexes before sharding. Okay, so optimize in database indexes before sharding. Okay, then optimize. Okay, friend. Use queue-based buffering for spikes. 1 minute. Okay, this is spike. We came to know. It's online, is it? Like use queue-based buffering for spikes. Okay, fine. Scaling options. Okay, fine. Right. Then, likely bottlenecks. In food delivery, restaurant menu reads, order rates during peak time, payment gateway latency, okay, delivery assignment processing, and the notification bursts, and tracking updates. What are scaling options we have there? Cache popular menu data, correct of products, for example. Use read replicas for read heavy data. Okay, scale stateless services horizontally. Increase event consumers for async workloads. Optimize database indexes before sharding. Use queue-based buffering for spikes. Okay. Senior level thinking. Do not start with sharding or complex microservices unless scale justifies it. Start simple. Observe bottlenecks and scale progressively. Beautiful. Performance thinking. What? Performance thinking focuses on latency, throughput, and efficient resource usage. Why? Slow systems hurt user experience and business conversions. Correct. When doing design of user-facing and high-volume flows. Performance sensitive area: menu browsing, search results, order placement, payment confirmation, tracking, updates. Optimization approach: cache, caching hot data, reducing unnecessary network costs, database indexing, async processing for non-critical tasks, payload size reduction, connection pooling, trade-offs. Caching menu data improves, caching menu data improves speed, but introduces cache invalidation and complexity. Fine. Then reliability and failure handling. What? Reliability means the system continues to work correctly even when some part fail. Why? Distributed systems fail partially, not always completely. When? During design, not after the incidents. Correct. Failure scenario, payment services timeout, order request is retired, notification release is down, delivery assignment is delayed, database latency increases, queue consumer falls. Okay. What is the protection mechanism we have for all that? Item potency keys, retry with back off, circuit breaker when needed, durable queries, dead letter queues, reconciliation jobs, then graceful degradation, clear error categorization. Okay, fine. Example, if payment succeeds but order confirmation fails due to timeout, reconciliation should detect and repair the mismatch. Okay, consistency and data integrity. What? Consistency and data integrity ensure the data remains correct across services and workflows. Why? Incorrect data can be worse than temporary downtime. Incorrect data can be worse than temporary downtime. Yes. When? For critical business operations such as orders, payments, refunds, and delivery status. Okay, then strong consistency needed. Payment confirmation, order final status, refund processing, inventory or availability checks where correctness is critical. Fine. Eventual consistency acceptable. Delivery tracking updates, notifications, analytics, use dashboard summaries. Example decision. Payment and order confirmation need strong consistency because duplicate charges or incorrect order status directly harm users. Tracking updates may be eventually consistent because small delay is acceptable. Security and access control. Security protects users' data and system behavior from misuse. Why? A system is incomplete if it works functionally but exposes sensitive data or allows unauthorized actions. When? Across all entry points and service boundaries. Security consideration, authentication, authorization, test boundaries, least privileges, encryption in transit, encryption the rest where needed, secure service-to-service communication, seeing sensitive data, making it law. Okay, a sensitive data should go to logs. Okay, fine, right. Food delivery example. A delivery partner may be authenticated as a valid user, but should only be authorized to update assigned deliveries. Okay, fine. Engineering view. Do not trust client supply the roles of IDs. Always validate permission. Always validate permissions server side. Okay, fine. Engineering view. Trust. Do not trust. The client supply the roles or IDs. Always validate permissions server side. Observability and monitoring. Oh, okay. What? Observability makes system understandable through logs, matrices, and traces. Why? Without observability, engines depend on guesswork, no chance during failure. When designed from the beginning, log, capture discrete events, order created, payment failed, status change, retry attempts, metric, track behavior over time, order success rate, payment failure rate, API latency, queue depth, error rate, traces. Okay, traces. Track requests across services, API gateway, order service, payment service, delivery service, notification service. Correlation IDs and correlation ID connects logs and traces across components as one order can be debugged end to end. Oh, deployment and operational readiness. What? Operational readiness means the system can be safely deployed, monitored, and recovered in production. Why? Good architecture can still fail due to poor deployment or misconfiguration. Why? A good architecture can still fail due to poor deployment or misconfiguration. Okay, when? Before production releases and during ongoing operations. Operation considerations, environment separation, externalized configuration, secret management, feature flags, canary rollback plan, dashboard alerts, run books, reconciliation procedure. A new order example, new order workflow can be released behind a feature flag, enable for a small percentage of traffic, monitored closely, and disabled quickly if error increases. So, okay, explaining decisions clearly. Explaining decisions clearly means communicating architectural choices as constraints, options, decisions, and trade-offs. Why? Interviewers judge clarity and maturity through decision explanation, not just component selection. When throughout the interviews, especially when comparing alternatives, decision explanation planning, constraint, opt lines, decision trade-offs, then future evolution. Example, a payment requires correctness. So I will keep payment authorization synchronous with strongly validated. The trade-off is trade-off slightly higher latency, but correctness matters more than speed here. The notifications can be asynchronous because delayed notification is acceptable. Senior level signal. A senior engineer does not only say what they choose, they explain why it fits the current constraints and what compromise they are accepting. Okay, fine. Common design pitfalls and how to avoid them. What common design pitfalls are mistakes that make a system fragile or interview answers weak. Why? Avoiding these pitfalls shows engineering maturity. When doing decomposition, data modeling, scaling agreement, and trade-offs discussions. Okay, then part pitfall number one, jumping into technology. Yeah, this we know too early. Pitfall number two, over engineering the MVP. Yes, that also we know. Then pitfall three, ignoring failure modes. Every real system has explained what happens when dependencies fail. Scaling everything blindly. Okay, this we know. Ignoring security. We have already discussed. Ignoring observability. We also discussed hidden trade-offs. We know this. Every design choice has a cost. Say it clearly. Yes, that's all. Complete food delivery end-to-end walkthrough. Clarity requirements, step one, clarify requirements, and then define MVP, identify main flow, define components, define data model, define communication, define scalability, define reliability, define security, and then define observability, then define operations, then finally explaining the trade-offs. Okay, start with simplest architecture that signifies current needs. Add microservices, sharding, multi-region, or advanced event patterns only when scale and operational maturity justify them. Okay, viral end-to-end system design flow. Okay, this is a visual effect. And then you have food delivery, visual again, food delivery, architecture flow, okay. Then decision explanation pattern, okay. Then these are the interview questions. Okay, yeah, fine, right. One-line summary. End-to-end system design is the disciplined process of moving from requirements to architecture, connecting every major design area, and explaining decisions clearly through constraints, then options, trade-offs, and future evolution. Okay, final outcome. After completing this module, learners should be able to run a complete system design walkthrough confidently by not there clarifying. Okay, sorry, clarifying requirements before choosing tools. Clarifying requirements before choosing the tool. That way, you should be very good in managing the tools. Defining MVP and scope very clearly possible. Mapping user flows architecture, yes. And then designing components, APIs, data and communication patterns, yes. Addressing scale, performance, reliability, consistency, security, observability, and operations. Then finally, explaining trade-offs in a similar level, sorry, in a senior level interview style. Oh my God, massive topics. Super. So much. Yes, Deepak.